Hi there, welcome back. In this slice of physics, we will take a look at interacting objects, and we will see what the forces are between objects that are in contact with one another. And we will learn how to use Newton's third law in determining forces in these situations. Let's take the example of three blocks that are stacked on top of one another. So here's the first one, here's the one that's sitting on top of it, and here's the one that's at the very top. Let's call them A, B, and C. And let's say their masses are 1 kilogram, 2 kilograms, and 3 kilograms, out to 3 significant digits each. And our job is to draw the free body diagram for each object and to figure out the forces acting on each object. So let's start with object A over here. Let me go back to the process we used before of drawing the circle around the object of interest to determine the forces that are acting on it. So that's my circle, and as I go around it, I can identify my contact forces. So there's a force from block B on block A, and as I go around it, there is no other contact force. So the only two forces acting on A are force of B on A and the weight of A, which is the force from the earth on A. The weight acts straight down as always, and the force of B on A, since it's a supporting force, it's similar to a normal force, so it'll act perpendicular to the surface, so it acts in the upward direction like that. And because block A is in equilibrium, these two forces will be equal to each other in magnitude, but opposite in direction, so they add up to 0. So our condition of equilibrium was sum of Fy equals 0, where this is my y-axis, and here's my x-axis. So this condition of equilibrium gives me plus Fb on A, because that's in the positive y direction, minus Wa, let's call this Wa, for block A, equals 0, and this gives me Fb on A equals Wa, which is Ma times G, and so that is 1.00 times 9.80, which is 9.80 Newton. So that's the free body diagram for object A, and those are the forces. Moving on to object B, let's do the free body diagram over here. So once again, I draw the loop around B and start going around it. The forces I have in this situation as I go around it are, there's a contact force here from C, which you might be tempted to call normal force, but we reserve normal force for fixed surfaces, so in this case we'll just call it Fc on B, and its direction would be acting upward. And we go around it, and here there's a contact between A and B, and you might be tempted to call that weight of A, but that technically would be incorrect, because the weight of A is a force that acts on A from the earth. A would be the object, earth would be the agent, and that weight of A will only show up on A's free body diagram, because remember, free body diagrams only capture forces that are acting on an object, and since weight of A is acting on A from the earth, that belongs in A's free body diagram. So in this case, we would simply call this force force of A on B, and that would act in the downward direction, perpendicular to the surface again. And those are the only two contact forces. And then the third force I have is a long-range force of weight of B, and that would act in the downward direction, and the agent for that is the earth. Now we see that the mass of B is twice that of the mass of A, so I will show the length of this arrow being twice, and so there is weight of B. The other downward force was force of A on B. Now here, let's talk about this a little bit. So we already had something called force of B on A, and now we have a force that's called force of A on B. These two forces form Newton's third law pair, and because they form Newton's third law pair, they will be equal in magnitude and opposite in direction. So here's Newton's third law pair identified. And so I can see that FA on B will be acting downward and will be the same length of the arrow as B on A was. So I show that over here. FA on B. And then I've got the force of C on B that's acting in the upward direction. So now when I set up my condition of equilibrium, sum of forces in the y direction is still 0 because B is also in equilibrium. And so now I have plus FC on B minus WB minus FA on B equals 0. And now I can put the values in. So I got FC on B minus weight of B is 2.00 times 9.80 minus FA on B we figured out was the same as FB on A, and so this would be 9.80. Notice that I did not change the sign. I'm just keeping the same value even though they're opposite in direction. And the reason I do that is because these variables, FB on A, FA on B, WB, all of these variables that we're working with only contain the magnitude. Their direction is taken care of by the sign that we put in front of them as we go through our free body diagram. So that's why that number just comes in like that. And so that sum equals 0. And I can solve this to say FC on B equals 2 times 9.8 is 19.6. Moving over to the other side, it'll become a positive. And then this will be a plus also as it goes to the other side, 9.80. And so this gives me a value of 29.4 Newton. And third, I've got object C to work with. So as I go around it, there's my circle. As I go around it, there are again only two contacts. The force of the ground on C, which is the normal force, the force of B on C over here. And even though you might be tempted to say that there is a force of A on C, this method tells you that that doesn't exist. A is not in contact with C, so there is no contact force between A and C, and the force between A and C can't be a long-range force, so there is no force of A directly on C. So my forces are the normal force acting in the upward direction perpendicular to the ground, the force of B on C acting in the downward direction, and the weight of C, which is acted on by the earth, and that acts straight down. That's my catalog of forces, and those are the only three forces. There is no force of A on C. A is not in contact with C. Now, the weight of C is 3 times the weight of A because its mass is 3 times. So let me draw this arrow as 3 times what the weight of A was. So something like that, weight of C. The other force that's acting in the downward direction is FB on C. Do we know this value? Well, let's go back here and take a look. We just figured out FC on B. So I know the value of this, and C on B and B on C are Newton's third law pair. So this guy over here and this guy over here, they are equal in magnitude and opposite in direction. And we got the direction captured by these arrows, and we'll take care of it in the signs when we set up the equations. The values of FC on B and FB on C only capture the magnitude, so they will be just equal to each other. So FB on C is about 29.4 Newton, so that would be something like this, FB on C. And then I've got the normal force on C that acts straight up. Okay, so now when I set up sum of Fy is 0 for this third object, I would get plus n minus FB on C minus WC equals 0. I don't know n yet, so I'll just retain it as a variable. I do know FB on C, that was the same as C on B. And since direction is taken care of by the sign, I just need the value, 29.4. minus the weight of C is 3.00 times 9.80. And the sum of all of that equals 0 again. And this simplifies to the normal force being 29.4 plus 29.4, which gives me 58.8 Newton. So this example was useful in a couple of things. It helped us learn how to use Newton's third law to identify pairs of forces that are equal in magnitude so we can work through them. Secondly, it helped us focus on what are the forces that act on an object and what are the forces that don't act on an object. So even though we're tempted to think that the weight of A acts on B, it directly does not, even though in this example the numbers worked out to be the same. If you want to convince yourself that this process will always work for every problem, all you got to do is take a situation where you tilt the floor and you get two blocks that are sitting on top of each other like this, and now work out the free body diagrams for the forces on these objects, and you will see that the weight of A does not act on B. It's the reaction to the normal force from B on A that acts as FA on B. This slice of physics helped us understand how to work with contact forces between interacting objects, and a key part of this was using Newton's third law to identify pairs of forces that are equal in magnitude and opposite in direction. Thanks for watching.